And we'll get started. First off, quiz questions. Uh, will we be allowed to use any other resources on the final? This immediately reminded me that I didn't actually give you the practice test last week, like I said I was going to. So I'll work on getting that edited and ready for you all later today. But short answer for the in-class part of the final, no. You're going to get a periodic table, the same conversion sheet and the equation sheet we've been using. And the periodic table will have electronegativity values, but those are the only resources you get on the in-class part. The take-home portion, which will be 2 questions. The take-home portion, you're allowed to use pretty much any resources you want, short of posting your question to an online forum or throwing it into ChatGPT or any AI. They all give the same garbage answers. So they don't work very well. So we'll talk about the rules for the take-home portion when we get closer to it, because I'm not going to give that to you early. But basically, it'll be one question that's multi-part question. That's here's some data, do some stuff with it in Excel, make some graphs for me, find the trend line, that kind of thing. Stuff that we practice. We're going to get more practice in this week's lab. And then there'll be one word problem on the take home as well. That'll be the other piece. Will be a more problem solving, write some algebra equations, do some conversions, do some stoichiometry with it, sort of word problem. How do we? There's also lots of questions on limiting reactants. So I think you all are still feeling a little shaky on that. Usually, if the bulk of the questions are on 1 or 2 topics, that means you all want to talk about that some more. So we'll keep practicing with that. If we have more than 2 reactants, how do we figure out the limiting reactant? Same way as you normally would. You see how much you're going to use. You either work on it, and we'll do the practice problems or the quiz questions in a minute as practice. But basically, it doesn't matter if you have 5 reactants and you have amounts for all of them. You take reactant 1, you see how much product you can make. You take reactant 2, you see how much product you can make, and so on down the line. Whichever one makes the least product is your limiting reactant. So it just makes it take longer if there's more than 2 reactants, but it's the same exact process. And almost always, if you have a reaction that has 3 or more reactants, one of them is going to be in a large amount of excess, usually. At least one of them is going to be obviously something you're not going to run out of. And we'll see some examples of that in the future. Is it possible to have 2 or more limiting reactants? Kind of. If you have 2 or more limiting reactants, the way that I would interpret that is you're running out of 2 things at the same time. So in our bread plus patty plus cheese makes a cheeseburger analogy. If you run out of bread and you run out of patties at the same time, but you still have extra cheese, the bread and the patties are your limiting reactants. Typically, in chemistry, one thing is going to run out first. But there are cases where the sig figs line up and it looks like you run out of both things at exactly the same time, in which case you would say they're both limiting reactants. Or if they're the only 2 reactants, you can say you don't have a limiting reactant, I guess. But saying that they're both limiting reactant is probably the most accurate. Does limiting reactant always have the lowest mass? No. Doesn't even always have the lowest moles. Because not only, so grams, we never want to think about it in terms of grams because things can have wildly different molecular weights, right? Which means you could have the same amount of mass of 2 different things, but if one has a much higher molecular weight, you have a lot fewer moles of it. And then even getting it into moles doesn't always answer. You can't just look at number of moles because you're not always using them up at the same ratio. Question about how do you know which side to start balancing on? It shouldn't matter. You balance wherever it makes sense for you to start balancing. if you do everything properly, you can start anywhere you want with any element you want on either side of the reaction you want. As long as you end with everything balanced before and after, it doesn't really matter where you start. So you can take sort of a guess and check approach. What I find to be make the most sense is to leave whatever elements, whatever compounds only have one element in it, leave that till the very end, because you can change that one without throwing off all the stuff you already balanced. If you start with the simplest things to balance and try to end with the most complicated molecule to balance, when you change that most complicated molecule, that usually means you're changing a bunch of elements at once. That's going to make your life a lot more complicated. So I usually leave the simplest things towards the end, for the end. But other than that, start wherever makes sense to you. So let's do practice. Let's do the quiz questions. I think most of you were at least able to get the mole to mole conversion. So we're starting to figure out where we balance this. This one's a little bit different of still a combustion reaction. We're still burning something with carbon and hydrogen, letting it react with oxygen to make CO2 and water. We'll go through probably on Wednesday. We'll start talking about how to classify different types of reactions. But so don't worry about that too much right now. What makes this one a little bit different is that our carbon hydrogen molecule also has an oxygen in it. So that's going to throw off our odd versus even approach. But we can still sort of guess and check. Start with the carbons. So I can say, okay, if I have one molecule of CH4O, also known as methanol, I can make one CO2 molecule, and I can make two waters. Total of 4 hydrogens on the left, so I need 4 hydrogens on the right. That all looks okay, except now we have the opposite problem normal. Now we have an even number of oxygens on the right-hand side, but an odd number on the left-hand side. So that tells us that something's got to be shifted. So without even touching the oxygens yet, I'm just going to say, okay, well, I know I've got an odd and even thing in here, so I'm just going to double this first thing, because one didn't work. Because I can't get to an even number of oxygens over here with it set up like this. So we double everything. 2, 2, make this into a 4. That's ugly, let me clean it up. 2, 2, 4. Now I've got a total of 4 and another 4, so 8 oxygens on the right. We have 2 there already, so I need another 6 oxygens, which makes 3 O2 molecules. If you're ever balancing a reaction and you think you have it balanced, but then you wind up with all even numbers on your coefficients, it might be balanced, but that means that there's a better way to balance it, because you could just divide everything by 2. In this case, if I'm looking at it, 2, 3, 2, 4, there's no like common denominator or anything there that I could reduce it by. So, and if we're counting, carbons look good, hydrogens look good, oxygens look good. All right, so questions on balancing. How many moles of CO2 when 2 moles of oxygen reacts? So this also brings up another quiz question somebody said, or somebody asked. I didn't get specific with oxygen means O2 here. If I just say oxygen, that means O2. We're talking about the names of the compounds. This is one of the reasons why we learned our nomenclature before we got into the reactions. If I say 2 moles of oxygen reacts, that doesn't include the oxygen as part of the methanol. That means just the O2, because that's oxygen. This methanol molecule has an oxygen atom in it, but it's methanol. It's CH4O. So that's not what I meant when I said that. So sorry I was not more clear with that, but just for the future, And then if it doesn't give you an amount, if it says 2 moles of oxygen reacts, it doesn't say anything about the CH4O, which usually means we're just going to assume that it's in excess, means we're not going to run out of it. Right? If you don't have details about one of your reactants, assume that it's in excess, that it's not going to run out. And if you're nervous about doing that on the test, right, I'm assuming CH4O is in excess because I don't have any information. You can always write your logic why you're making the assumption you're making on the test, and that lets me give you more partial credit even if you're wrong about that assumption. Right? Noting your assumptions is a big deal. So if we have 2 moles, call it 2.0 of oxygen reacting, and I want to know how much CO2 for every 3 moles of oxygen, that's 2 moles of CO2 just from the balanced reactions. Right? So all of these stoichiometry steps are always just making a conversion out of the coefficients, out of the balanced reaction. So that'll be 4/3 or 1.33 moles of CO2. Questions so far? When we don't need to worry about what's running out first, and I already give it to you in moles, not too bad, right? So what if that made it more complicated? How many grams of water are produced if 15.0 grams of methanol react in excess oxygen? If you're not sure where to start with putting all the numbers that you know into moles, right? Because we can't do this step in grams. So first things first, put it in moles. 15.0 grams of CH4O. We need the molecular mass or the molar mass of methanol. So 12 plus 4 is 16 plus another 16 should be 32 or so, 32.05 ish. One carbon is 12.011. 4 hydrogens, each hydrogen is 1.008. Hopefully we're all feeling pretty good about doing molecular masses by now after last week's lab. But if we want to show our work, four times 1.008 grams per mole plus 1 oxygen, so 15.999 grams per mole. We good with that? Is it daylight savings throwing everybody off too? Or is everybody just spent this time of the quarter? It's even more quiet than normal in here. All right. So ideally, if we had more sig figs on our mass here, we'd want more sig figs here. We never want to let our atomic mass or our molar mass be our limiting number of sig figs if we can help it. Right? But as long as I only need 3 sig figs on our mass there, 4 sig figs here is good, and I can do that one in my head. I know it's close enough to that. When in doubt, just write all your sig figs on your molar masses, and then because, like I said, we never want that to be our limiting factor. CH4O. We could stop there. Sorry, that's the way we've been doing it, right? Put it in moles and then leave it. We're going to get a number a little under half a mole, right? If you're starting to feel more comfortable with with our stoichiometry problems, if I know I'm not dealing with any limiting reactant or anything like that, I'm just trying to get a theoretical yield. If I'm comfortable with this step, I can just keep going. Because I can say for every, pull the coefficients down, for every 2 moles of CH4O is, oh, sorry, it's grams of water, not CO2. So it's 4 moles H2O. Right? So things are still canceling out just by doing multiple conversion steps for length at the same time. We've got our molar mass first, and then our stoichiometry step second. And if we wanted to, we could even do the last step to go from moles of water to grams of water, 15.02. So because we know the formula of the water is H2O, just like with our hydrate slab last week, we can figure out how many moles of water we have. So you can write it out all as one conversion if that's convenient for you. So we should get something like 0.5 times 2 is about 1, so something around 18 grams. I think it was what, 16.9 on the auto grader. All right, how do we feel about these mass to mass stoichiometry? Shaky. When in doubt, don't try to do it all at once. Right? If you're still feeling shaky about this, stop when you get it from moles of methanol and then do your stoichiometry step and get an answer in moles of water, and then do your atomic mass of water. Right? But your overall goal doesn't change whether you're doing it in one step or doing it on 3 steps. Get your grams of reactant into moles of reactant to moles of product to grams of product. All right, questions here? Then I had lots of questions on this one. This is an even better one for practice because we have to remember our nomenclature while we're at it. All right, so let's work through this one. I'll give you, if you don't have your notes out, actually, whether you got this one right on the, you don't know if you got this one right yet. I would start with a blank piece of paper either way. Let's start from scratch, get some practice, go through the process, even if you did it already for the quiz. Lithium metal reacts with aqueous zinc nitrate to form zinc metal and lithium nitrate. Let's start with the reaction, balance it, and then put everything in moles. How did I know the right ratios for these ionic compounds? How do I know it's 2 nitrates for every zinc? That Handbrook?
Because when you balance out the equation, it comes out to 2.
Right, because we know that because we memorized our polyatomic ions so well, we know that the charge on zinc on nitrate is -1. When we check on the periodic table, we remember that zinc is in the D block, but it's one of those ones that's the exception where we know the charge for it. So we know that zinc is 2+. Right, so good review all the way back for charges, balancing things out, remembering our polyatomics, etc. All right. Next step, balance it. There's a tip when it comes to these polyatomic ions. If nothing is changing about your polyatomic ion, like on the reactant side, we have the only nitrogen is in the form of nitrate, and the only oxygen is in the form of nitrate. On the reactant side, we still don't have any nitrogen or oxygen except for nitrate, right? So basically the nitrates aren't changing. If my nitrate is not changing into anything else, we don't have to balance nitrogens and oxygens separately. We can just balance nitrates. We only need to think about the nitrogens and oxygens separately if my nitrate is turning into like oxygen gas and nitrogen gas, or changing the nitrogen into some other form. As long as I know that that polyatomic ion is staying as a polyatomic ion, don't mess with nitrogen or oxygen being separate. Just say I have 2 nitrates there. So I know I have to make 2 nitrates over here. So I can do that. Which then means I can do this. Nitrates are balanced, lithiums are balanced, zincs are balanced. And as long as nitrates are balanced and there's no other oxygen or nitrogen, our nitrogens and oxygens are balanced too. All right, now we've written this problem out in a way that 1, our reaction's balanced, and 2, this is the format we're going to get used to for stoichiometry problems. Write out your reaction, make sure it's balanced, and then just write everything you know underneath the relevant compounds. Just a way to organize our thoughts before we start doing any math. If you get really used to putting it in this form, no matter what, the final will make more sense too, because the 3 stoichiometry problems on the final are going to be written just like this too. I'm just not going to do the balancing for you. So if you get used to doing your stoichiometry problems like this, it'll look really familiar. Right? Good test taking strategy is make sure you're practicing your problems in the same format that they're going to show up on the test. And then you don't need to have to worry about translating things around and moving it into the form you're used to thinking. Just get used to thinking in the way that it's going to be on the test. So if we use molecular weights, lithium's molecular weight's about 6, so this is going to be about 1/4 of a mole. And zinc nitrate's a lot larger molecule. Who can give me my moles for lithium? 0.216. Oh, lithium's got a 7, not 6. Huh? That makes more sense. And then zinc nitrate. All right, from a logic point of view, we can look at this and we can tell what the limiting reactance is right away. What's going to run out first? Yeah, not just because we have fewer moles of it, but we have fewer moles of it and we're using it up twice as fast. Right, so though if we have the least amount here and we're using it up twice as fast, we can tell just by looking at it. If these two numbers were reversed, it would be a little bit harder. We'd want to show our work. And so it's not a bad idea also to not try and do it by intuition yet. Get the process down. So if I have 0.216 moles of lithium, we're trying to figure out how many grams of zinc metal. So we're trying to get that answer there. Let's just figure out our theoretical yield for from both of these and see which one's less. Right, so moles of lithium for every 2 moles of lithium, that's 1 mole of product of zinc. So 0.108 moles of zinc. And if I do the same thing with the zinc nitrate, it's going to be 1 to 1. 1 mole of zinc nitrate is 1 mole of zinc product. So we have enough lithium to make 0.108 moles of zinc, and we have enough zinc nitrate to make 0.245 moles of zinc. So which one is the real answer? Right, the smaller number, the smaller theoretical yield. If you use this approach, whichever one makes less product is the one that's going to be your limiting reactant. When you get lost at some point, you're going to feel like the right answer is to add these together at some point. That's a normal thing. People like, I don't know what to do, but I have 2 different moles of zinc, so I'm just going to add them both together. Don't do that. Right? Think about hamburgers. I have enough patties to make 108 hamburgers, and I have enough pieces of bread to make 245 hamburgers. I'm going to run out of patties first, and I'm going to be limited to 108 burgers. Any guesses? Because it's 1 to 1, we don't necessarily need to put the parentheses around the nitrate. We needed the parentheses around the nitrate here so we could show that we had 2 of them. So you can just leave it like that. It's not wrong to do that, but it's just unnecessary.
Okay.
It's implied that you only have 1 of them if there's no parentheses. All right, so the last step for this one was just, okay, once I know I'm going to be able to make 0.108 moles of zinc, we just use the molecular weight of zinc to figure out how many grams that is. Right, so just undoing the part we did here. Good. Since we skipped over the getting to the moles here, we'll show the step at the end, 0.108 moles of zinc. And for every 1 mole of zinc, it's what, 65, I think? So we're going to get something in the 6.5 7 grams range. All right, how do we feel about these? Starting to feel like this is a process that you can wrap your head around. It's putting together a bunch of the stuff we've already done, but it's mostly the same thing every time. Get it in moles, convert it to something else. Once you get it to something else, get it back to grams or back to, we're going to talk about gases today, how we can get from measured values of gases and put it into moles. But basically the rest of this class, what I'm going to add from here on out is different ways to get to moles. Next week is going to be all about concentration and pH. Those are just different ways we have of getting to moles, but the stoichiometry step doesn't change. All right. So we're going to talk about gases today. And before we start talking about this, we should talk a little bit about what a gas is and how we measure it. So for starters, what is the difference between a gas and a liquid? Or a gas and a solid? Any ideas? The amount of kinetic energy the molecules have. We said that when gas molecule or when molecules have enough kinetic energy that they can kind of break free from their surroundings, that's what makes it a gas, right? When we talked about phase change, we talked a little bit about that, about how I think I have another one of those. Those PhET simulations. So this is the same one that we did when we looked at same service that we used for that Vesper lab. It's out of University of Colorado, my alma mater, so I feel strongly about it. But there's just all these free animations that are good for playing around with different aspects of physics and chemistry. If we have something like a solid, the atoms, the molecules are still wiggling around a little bit. You see it's not perfectly steady, but none of those spheres really have enough energy to really move around. So it mostly holds its shape. If we give it a little bit of heat, it starts to lose its shape a little bit more, right? Now all of a sudden they're still all grouped together, but there's a little bit more wiggling happening. And you notice it starts to lose that square shape. It was kind of in a cube shape, but now it's going to start, especially if I give it a little bit more neon I'm looking at. So it's still mostly all stuck together, but it's definitely not a square anymore, right? So we basically just went through the phase change from a solid to a liquid. They're still mostly stuck together, but they can move around a lot more. But these little bits up here, that's what a gas looks like. Basically, a gas molecule is when you have enough kinetic energy that on average, all of these little spheres are all freely moving. They're able to just sort of move around and bounce around, bounce off the walls of the container, and they're, for the most part, evenly dispersed. All right, and it looks a little bit different. So this will actually even show you the phase diagram. We're sitting here in between liquid and gas phase right now. We're right at the boundary. It's kind of going through a phase change between a liquid and a gas. If I increase the temperature or if I decrease the pressure, can't decrease the pressure, I can only increase it from here. I can change where it is on that phase diagram. That's not what I want to spend most of our time on today, though. I just wanted to start looking at the idea that these gas molecules are going to be different than solids and liquids because they're basically totally independent from each other. You can think of them as just like ping pong balls flying around a room. If that ping pong ball happens to hit another ping pong ball, they bounce off each other and continue on their way. Right? For the most part, we're going to assume that these gas molecules are free to move about and are not interacting with each other. There's a lot of space between these different gas molecules. What happens when those ping pong balls bounce off the edge of the container? When they hit the wall of the container, do they break free through the wall? They bounce back the other way, right? Well, if the wall is acting on the ping pong ball is also putting pressure on the wall, right? It's putting force on the wall, which seems really, really small, especially on the scale of individual molecules. But if you think about just having a big box with all of these spheres bouncing off the walls all the time, if we add up all of the different force that these different ping pong balls are putting on the container, there's actually a measurable amount of force that's being exerted by the gas molecules on the container itself. Right? And that's one of the things we refer to as what. So if we add all of that up and we go to our physics definition of force, force is a mass times an acceleration. So because these gas molecules have mass, when they change direction, they have acceleration. So force, there was a force that acted on these gas molecules. If we add up all of the gas molecule forces over a period of time, let's just call it a second, there's going to be a whole bunch of collisions with the walls all at the same time. All of those forces put together is the total force that's pressing outward from the gas. Right? Think about blowing up a balloon. Does the balloon inflate itself? You have to put energy into the balloon to inflate it, right? You have to add gas molecules into that balloon, and then those gas molecules bounce off the inside of the balloon. That's what helps it keep its shape. If we add up all of the gas molecule forces, we get a total amount of force. But if we want to normalize it based on how big the container is, we actually get something called pressure. So pressure, the physics definition is it's a force divided by an area. Right, so notice the difference in A. Lowercase a is acceleration. Uppercase a is area. This is going to be important in this week's labs. We're going to do some experiments with pressure, where we're going to calculate it using these equations. So if you have a whole bunch of gas molecules bouncing off the inside of this container, this force number might be kind of big. But if you have a very large container, the overall pressure can still be small, right? The larger the container, then the lower the pressure is. So to give you an idea of the difference between force and pressure, because this isn't a physics class, force is the total amount of mass that's accelerating. When you divide by the area, that creates a very different property. So has anybody ever had a friend walk on your back as a form of a back massage? It was a common thing, and when I was in high school, you'd lay down on the ground. Maybe it was just the wrestlers, but you lay down on the ground and have somebody walk all over your back. Felt really good. That works as long as they're barefoot, right? What happens if they put on high heels and do that? They weigh the same, but that doesn't feel the same, right? If they weigh the same, then this force piece didn't change. but the area that you're putting the force on is a lot smaller, so the pressure goes up. Right? The other example is using a knife. If you use a knife to cut something versus trying to cut it with the side of a fork, you can put the same amount of force into something, but the edge of the fork is a lot bigger, has a lot more area than the blade of a knife. Same amount of force on a knife blade cuts evenly, nice and evenly through your food. But trying to cut it with a blunt object, you're really just ripping it, right? Even if you're using the same amount of force, right? So when we're talking about or pressure in gases, we're basically not going to talk about force with gases, because if we wanted to talk about the overall force, we'd have to either add up all of the individual gas molecules and find their mass and how their acceleration changes when they bounce off the inside of this container, or we would have to know the entire inside of this container. If we knew the entire area here, then we could sort of sum it up backwards. But basically with gases, we only talk about pressure because the number of gas molecules is just too high. We can't sum up all their forces. We can just get an average force if we think about it in terms of pressure, right? So pressure units in general, the simplest pressure units are in the form of a force divided by an area. What's an example of a pressure unit that's a force divided by an area? PSI. PSI stands for pounds per square inch. Pounds is a force unit. In the sciences, we usually write it like this because we actually are going to look at the units. We don't usually write it as PSI in the sciences because we can't really do any conversions with this. This actually would allow us to use the force or this pressure as a conversion if we wanted, if we knew the total area and we'd use the force, we could actually figure out the total number of pounds being pressed on that. So we usually write it this way. Does anybody know what standard pressure is in PSI at sea level? What is atmospheric pressure? That's going to be in inches of mercury. We're going to talk about that unit soon. That's a common unit for meteorology in the US, uses inches of mercury. PSI is 14.7 at sea level. Right, and this is on your conversion sheet too. Your conversion sheet has a pressure section. We're basically going to say there's about 5 really common pressure units, and we're going to define them all relative to 1 atmosphere. So we can have pressure units that are based on force over area. And then we have other pressure units that are just defined by standard. So we're just going to say that all of these other pressure units are equal to 1 ATM or atmosphere. 1 atmosphere is basically what we just decided was the average barometric pressure at sea level on Earth. So we just define everything else relative to that. So 14.7 PSI is equal to 1 atmospheric pressure. What other force or area units could we use? We don't really want to use imperial units if we can help it, right? What are the metric units for area, for starters? So the metric unit for force is a Newton, and the metric unit for area is a square meter. So a Newton per square meter is another common pressure unit that's based around the same, it's a force divided by an area. But in the nature of SI, instead of calling it newtons per square meter, we give it a new name. We call it a Pascal. after one of the physicists who first did some of this research. Interestingly enough, this is the same Pascal. If you take any math where you look at combinatorial stuff or probability, if you've ever heard of Pascal's triangle, it's the same Pascal. It's a French human named Blaise Pascal. He's also a very influential theologian and philosopher from the 1600s, I'm pretty sure. You spend much time in theological discussions, you may have heard of Pascal's wager. That's that same Pascal. And Pascal's triangle is based on probability, which is basically if you make a triangle of integers where you just add, well, we won't get into that. We don't need to get into probability. Yeah, you add the numbers above it together to get a new piece. A Newton is really, really small. A square meter is a lot bigger than a square inch. And a Newton is a lot less than a pound. So there's a lot of pascals in one atmosphere. In fact, it's 101,325 pascals is one atmosphere. Again, this is on your pressure. Kind of, except that we're talking about the internal surface area of the container. We'll talk about volume and how that relates. It turns out that volume does factor into this. We're going to measure our gases in terms of volumes, but we define our pressure in terms of areas. All right, so we've got one atmosphere is 14.7 psi. We've got one atmosphere is 101,325 pascals. If you want to stay in pascals, but you don't want to deal with having such a big number here, they also just redefined this. If you take pascals and you divide by 100,000, you get bar. If you've ever heard of bar in terms of pressure, 0.5 bar or something like that, bar is short for barometric. And it's basically take pascals divided by 100,000. So 1.01325 bar is one atmosphere. 1 bar and 1 atmosphere are really close together. They're off by about 1%, which normal fluctuations due to weather will throw off your barometric pressure by that much. So you could say that 1 bar is pretty similar to our average atmospheric pressure as well at sea level. Not up here. We're at about 0.8 atmospheres up here. All right, so we've got PSI. We've got atmospheres. We've got pascals and bar. The last one is a little bit weird. And the last one it's a little bit weird because it was the first type of pressure that they actually figured out how to measure when it came to atmospheres. Basically, the first person to design a barometer did so because he realized that everybody's always has put your thumb over the top of a straw when it's in your drink. Then you pull your straw out, and your drink stays in the straw, right? Why does that happen? It creates a vacuum if it starts to fall out, right? You can even do this with next time you're doing dishes. If you fill up the sink in your kitchen, take a water glass, fill it up with water, and then tip it so that the closed end is up. The water stays in the glass when you do that, right? What's keeping it in the glass? Turns out, so you're right to think that it has something to do with the fact that there'd be a vacuum in the top otherwise. But that shouldn't really matter. Gravity's still pulling it down, right? So it's not the fact that it would create a vacuum that keeps the liquid in there. It's the force of the gas molecules pushing down on the water itself. So if you think about
pushing it back up into the straw.
Yeah, so if you think about filling up a container with water, if you take a water glass, the water will stay in here as long as you keep the rim of the glass below the water, right? Below the surface here. That's because the gas molecules are all bouncing off this water and pushing on it. If you drained the water out of this and created a vacuum there, there's no water molecules there, or sorry, there's no gas molecules there to equalize that pressure. So go back to your thumb on top of the straw. What happens the second you remove your thumb from the top of the straw? Liquid falls out the bottom, right? Because now you've got the same gas pushing in up here as you do right there. So an Italian physicist named Torricelli figured out that if you just extend this, what's really happening is that if you extend this to the point where the weight of the water that's stuck in this container is equal to the force of the gas molecules pushing down, you actually can create a vacuum. Once you get a certain height above the surface of the water won't continue rising. You can do this with a garden hose. If you fill a garden hose up with water, cap one end of it and raise it up, you have to raise it a long ways above the surface, but there comes a point where the water won't continue to rise when you lift up the container anymore. So instead, you get something that looks like this, where the height is based on the height where it stops rising is based on how many gas molecules you have pushing down on the surface here. The problem is this height, if you use water, because of water's density, this height has to be about 30 feet. You have to get about 30 feet above the surface of the water before this stops happening, which is why it seems counterintuitive, because we never have a straw that's 30 feet long if we're putting our thumb over the top of it, right? Or a water glass that's 30 feet tall. In theory, it would work though. You can make a barometer made out of water where you measure this height, and that height gives you the atmospheric pressure. So the other unit that we use all the time in chemistry is based on this, except that instead of using water, we use a liquid that's more dense. Any guesses? What liquid do we have that would have been common enough in 1700s? It's exceptionally dense. Mercury or lead. You can do this with lead, but you got to melt the lead first. Mercury is already a liquid at room temperature. And actually, mercury is even more dense than lead is. Lead's about 11 grams per cubic centimeter. Mercury is 13.9. If you make a pool of mercury and stand a closed tube up like this, the height where it stops rising under normal atmospheric conditions is 760 millimeters if you're using mercury. So millimeters of mercury is also a pressure unit. And this is still to this day, this is our most accurate way of determining the barometric pressure on a day-to-day basis. We have a mercury barometer in the lab. And it's literally this same design. It hasn't changed since the 1600s. Since Torricelli first discovered how to make a mercury barometer. We just use a really small container of mercury down here in a really narrow tube so that we don't have to have a ton of mercury around. But that number, 760 millimeters of mercury, is a pressure unit. And if you convert 760 millimeters into inches, you get something around 31 inches. So if you've heard of inches of mercury as a barometric pressure unit in any like meteorology apps, if you check your weather app, if you check the barometric pressure, it'll usually get reported in inches of mercury if you're in the US. But it's literally just measuring this distance where the mercury stops rising when the glass continues to go up. All right, so what does that mean? Here's our conversions. I'm just going to recap what's on your conversion sheet. Exactly 1 atmosphere of pressure is equal to about 14.7 psi, 101,325 pascals, 1.01325 bar, 760 millimeters of mercury. Is there one more I'm missing that we wrote earlier? I think that's it. Those are the 5 big ones for this class. I don't put inches of mercury on your conversion sheet because you know how to convert inches to millimeters. So as long as you know millimeters of mercury. Oh, that's the other one. This gets redefined oftentimes because millimeters is confusing. If you're not used to thinking of it like this, you might think that's a distance when really it's a pressure unit. So they also call that torr. After Torricelli, who discovered it. Right, so this is another one of those one-to-one conversions where you don't even need to show your conversion step, like cubic centimeters to milliliters. Millimeters of mercury is the same as torr. And these numbers are exact. These are all measured. So sig figs factor in here. But 1 atmosphere and 760 millimeters of mercury are defined as, 1 atmosphere is defined as exactly 760 millimeters of mercury. So those ones are exact. All right. I think that's everything we need to start talking about pressure. Like we haven't been talking about pressure for the last 25 minutes. To start talking about pressure just more specifically. But let's go ahead and take our break. Let's come back at 25 after, and we'll start figuring out how all this applies to gas molecules. Okay.
What are we doing? How these numbers, the one I'm trying to find out.
Okay. So let me go back. So we have 1.50 grams of lithium. If we want to get to moles of lithium, we're just going to use the periodic table. So lithium's atomic mass is 6.94. So we just say 6.94 grams is 1 mole of lithium. Yeah, so the coefficients don't affect the molecular weight. They just affect how many moles get used. Common mistake. Yeah.
Did you talk to Steven about? I called him and said, like, I was like, and I want to know about it. And then Steven ended up texting them, so nobody knows. But Steven will write you back. There's Steven. There's so. That's why that's so. Where's the friends? We're not the friends, not that it exists. We're not gonna have a liar or something. And so I really needed that advice for that. I did, she for it to also be that, but if hiring Susan Stacy, friend of Stacy, it's where we can fall down the head. I'm sure you kind of even walk down that way. Yeah. He's so good to see it. Keep it. Sounding like a crazy bitch, so maybe I'll start members. Because that's serious for Sam. Like Steve does get it. He was not, and I've said that, but I mean, I think I look for like a high percent. But it's not really to it. It's not sitting properly. There's one that you know. Fine, so we can probably or out. You know, like for everyone else. They will see that. My dad said that's what from some trees. At the same time. I don't have any sense, but. Around it. It's not even this. It's not really about it. Right, but no. You don't need to get irritable, miracle on. Sorry, I spoke up. Because miracle has. He's like. But. It's more like this is down or then when it's breaking. Yeah, switch this. And then you're afraid. I love it.
All right, I know we still have some people not back yet, but we're gonna go ahead and get started thinking about how pressure and volume interact together. So let's say we've got system looks like this. We use these a lot in gas laws or when we're studying gases. This is just called a piston. It's just a closed cylinder that's closed on one end and the other end is allowed to freely move. So we're assuming it's frictionless. We're assuming no gas can escape around the outside of this. If we have this closed container that's 10 liters, let's pick 10, it's a nice round number. What do you think happens to the pressure if you cut the volume in half?
Increase. Sir.
The surface area is decreasing. And remember, pressure is force over area, right? So if our volume is decreasing, we cut our volume in half. there's a slightly different relationship between volume and surface area. But essentially, if we cut our volume in half, we're going to cut our surface area in half as well. We can make that assumption. So if we cut the surface area in half and we keep the force the same, what should happen to the pressure? It should go up by how much? It would make sense for it to be a factor of 2, right? If we cut our volume in half, that cuts our surface area in half, so our pressure should double. And we should be able to do that indefinitely, right? We cut our volume in half, our pressure doubles to well, phase changes is 1. If we keep pushing this small enough and small enough, then eventually we're going to force it to be a liquid instead of a gas or a supercritical fluid, where things have enough energy to be a gas but not enough space. But we're going to treat this like what's called an ideal gas. In an ideal gas, we have 2 assumptions. One of which is that it won't go through a phase change. Or more specifically, we're assuming no intermolecular interactions. In other words, we're going to treat these ping pong balls bouncing around like they're truly ping pong balls, when really they might be more like, depending on what the gas is, it might be like, you know, my kids are obsessed with those like little fidgets that you squeeze needles that have like the sticky on the outside. They're awesome. Then also, if I throw 2 needles at each other, they're not going to actually bounce off, right? Because they're soft and they're a little bit sticky. They have some interaction between the molecules. So we're assuming that they're going to be more like ping pong balls than something more sticky, which means it won't go through a phase change. The other assumption that we make, well, let's think about, so if we're assuming no phase changes, we can keep this going out forever, right? But could we ever actually get to a volume of 0? If we keep cutting our volume in half and cutting our volume in half and cutting our volume in half, we'll never get to 0, right? Every time we cut our volume in half, the pressure doubles. So practically speaking, there's no point that we could actually get to a volume of 0, even if the gas molecules themselves have 0 volume. So that's our second assumption. Gas molecules have volume equal to 0. So basically, it doesn't matter how much you squeeze on this, we're assuming that the gas molecules themselves are not taking up a significant amount of the total volume. Right, and so these are the assumptions. We're going to go over these again, but anytime we're talking about these gas laws and we're doing these thought experiments, we're making these assumptions. We're assuming it's not going to go through a phase change and the gas molecules themselves have a volume of 0. So with that in mind, we could keep going further and further and further, except that then the pressure is going to get higher and higher and higher, right? The closer we get to a volume of 0, the more the pressure is going to go towards infinity, right? Because this number is getting smaller and smaller. And we can never actually get to 0 because then we'd have we'd have a dividing by 0 error. But if you've taken calculus, which is not a prereq for this class, so don't worry about what I'm about to say if it doesn't make any sense to you. The limit of this function as it approaches 0 is infinity, which is another way of saying that the closer our volume gets to 0, the more our pressure gets close to infinity. And we can't actually have an infinite pressure. So basically, there's a practical limit here, even if we didn't have phase changes. So what about if we go the other way? What if we started here and we started doubling the size? What should happen? If we're doubling the volume, we're doubling the area, right? So if we double the area, our pressure should get cut in half. And so we get a function that looks something like this. If we keep doubling the volume, doubling the volume, doubling the volume, can we ever actually get to zero pressure? No, no matter how big you make the container, there's still going to be some tiny probability that a gas molecule bounces off the side. If the gas molecule bounces off the side, this force is not zero. So it doesn't matter how big the area is, we can never actually get to zero pressure. Turns out a vacuum, a true absolute vacuum, doesn't exist. Even in deep space actually has a measurable atmospheric pressure. It's just really, really small. I want to say if you go with the definition of deep space that the astronomers use, which has something to do with going past the magnetosphere of Earth or something like that, you get pressures that are something like 10 to the minus 7 torr. And for comparison, remember, torr was 760 torr was 1 atmosphere pressure. So it's 10 to the 9 times smaller, which 10 to the 6 is million. So a billion times, a factor of a billion less gas molecules in deep space than there are on Earth. But still a measurable pressure. We can still actually measure that number. So it doesn't matter how big your container gets, you're still going to have some pressure. What does this type of function look like? If it's got an asymptote at 0, where this starts going up to infinity, and it's got an asymptote at 0 here, it starts going out to infinity. Who's taken their algebra recently enough, they can tell me what parent function that is. What type of function gives you that shape? Y equals 1 over x. As x gets bigger, y gets smaller, but you can never actually get to infinity. And then as y gets bigger, x is getting smaller. So our initial assumption is that this function, if we plot pressure as a function of volume for a closed system of gas, we get something that looks like this. There it goes. Right, and so the way we write it as not y's and x's, say that pressure is, we don't say is, this symbol here is a mathematical symbol meaning proportional. Proportion, I always mix those up. Which just means that it's equal to some constant. We use lowercase k a lot, times 1 over volume. In other words, when volume gets bigger, pressure gets smaller. When pressure gets bigger, volume gets smaller. Right? The reason I'm using this symbol instead of just saying is equal to is because this actually gives us an interesting math relationship here. We say that pressure is equal to some constant times 1 over volume. For any closed system of gas, then we can rearrange that to look like this. Pressure times volume is equal to a constant. Still doesn't seem all that useful because this constant is going to change depending on what your system of gas is. But for any system where we have a closed container of gas at a constant temperature, if your pressure goes up, your volume goes down and vice versa. Right, so this leads to what's called the simplest, or a simple gas law. This is called Boyle's law. Any combination of pressure times volume is equal to every other possible combination of pressure times volume if it's a closed system of gas. And so here's our atmospheric or our pressure conversions for the sake of doing this problem. So let's say we have a 750 ml bottle and it's sealed at 760 torr and kept at a constant temperature. So you have an empty bottle, you sealed it at sea level, and then you kept it in your car, so the temperature didn't really change. What is the pressure in PSI if the volume expands to 1.65 liters? So the way we do this, anytime we're using these simple gas laws, they're always going to be about a change. It's always going to start the same way. You have a system of gas that's sealed, and then here's your initial conditions. Then you change something. What happens? All right, so our initial volume, V1, is 750 milliliters, which since our next volume is in liters, we might as well put it in liters. Our initial pressure is 760 torr. The question says, what's the pressure in PSI if the volume expands to 1.65 liters? So our final volume, V2, is 1.65 liters. If we know initial pressure, initial volume, and final volume, we can find final pressure by doing a little bit of algebra. So you do the algebra before or after you plug in the numbers. I solve for P2 first. I get P1 V1 over V2. We just plug everything in. 760 torr times 10.0 liters, or sorry, 0.750 liters. That was the last example. Divided by 1.65 liters. What's going to happen to our units? We're in torr. We've got liters there and liters here. Liters is going to cancel out, right? So our final pressure should just be in torr. If your units don't cancel out, then you did something wrong. You got to start by doing a conversion somewhere, right? We want our units before and after to be the same so that they cancel out. Otherwise, this doesn't work. Doesn't matter what volume units you use or what pressure units you use, as long as you're consistent. So let's see, we more than doubled that, so we're gonna cut this in half. If that three, somewhere around 340 maybe. What is it? 25 or 45?
45.
Thank you. My ears are a little bit plugged up because I've got a bit of a sinus infection or something. Easy enough. Just a little bit of algebra and paying attention to units. Except as long as we're paying attention to units. Question did ask about our final pressure in PSI. So we have to do a quick conversion. 315 torr. What conversion are we going to use here? Yeah, the nice thing about setting all of these equal to the same standard pressure is you can make a conversion factor out of any of these. Just pick the one that you want to cancel out, put it on bottom. And then we want PSI on top. So 14.7 PSI goes on top. Brooke? Sorry. Yes.
So can or not have a decimal? Because I got 345.45.
So torque can have a decimal because it is millimeters, so it is like measuring a length. We just cut it to 3 sig figs because we only had 3 sig figs there and there. And then I guess technically I should have specified that that's 3 sig figs too. All right, so we'll get something in the 6 range.
6.67.
6.67. All right, so these simple gas laws, they're called simple gas laws because they're not because it's always entirely easy to use them, but if you pay attention to your units, they're always going to be 2 variables before a change equals 2 variables after a change. Right, so this is Boyle's laws, pressure and volume. The next law is Charles' law. And Charles' law has to do with what happens when we change the temperature. So in this example, we don't really want to change the temperature with a constant volume, because if you seal a container and then a container full of gas and then you heat it up, that's not a good thing, right? That's a good way to cause an explosion. We don't want to do that. So the way that they set this experiment up is with a piston like this, we sealed this up and then we changed the temperature. And the fact that the piston is allowed to freely move means that the pressure stays constant, but the volume changes. Right, and this is actually very similar to what an internal combustion engine does. So if you have this piece of the piston that moves up and down is attached to a drive shaft, this is how you generate force with an internal combustion engine, is using gas laws. So what do we expect would happen if we increase the temperature? What's going to happen to the volume? Seems like it should go up, right? Has anybody ever taken a balloon and held it over a candle? It gets bigger first, and then it pops. Right, so we would expect that because, and if we think about why that is, pressure is equal to force over an area. Well, when you're increasing the temperature, you're changing the force. If you keep the volume constant, then A stays constant. But from a logic point of view, we can see, okay, if we're increasing the force of every individual molecule, by increasing the temperature, the volume's got to expand because they're hitting the walls harder. Same number of collisions, but they're hitting with more force. So that means that every individual gas molecule is going to basically take up more space. You need more space per gas molecule if the temperature goes up, is our hypothesis. So we could assume, we might assume that it looks something like the other one, where if we double the temperature, we're going to double the volume. Except when we actually do the experiment, we get a line that looks like this. Why is that the case? How come it doesn't go through zero? Can you have a gas that's colder than 0 Celsius? I mean, I don't know about you all, but I was able to breathe just fine this morning, right? It was colder than 0 Celsius this morning when we woke up. There was still gas around. So what's happening here when we double these temperatures in Celsius, the volume's not doubling because we're not doubling the actual force. Where would we want 0 to be if we were going to doubling the force doubles the volume? We already defined it when we started talking about energy. Remember how we talked about how energy, kinetic energy of these molecules is tied to temperature, right? But kinetic energy doesn't stop at 0 Celsius. Kinetic energy stops at 0 Kelvin. So this is actually the first experiment that led to them having a number for 0 Kelvin, for absolute zero, was they did this experiment and they said, okay, well, when we increase the temperature every 25 Celsius, we get a straight line for the volume of this gas. But it doesn't start at 0. If we extend this all the way back until it hits 0, which actually be probably somewhere about there. I was trying to keep this to scale. That's when the volume would go to 0. That's when all molecular motion stops. That's where we get our definition for absolute zero. So basically, if we do this in Kelvin instead of Celsius, we do get a straight line that goes through 0. We can't get all the way to 0 Kelvin, so we can't actually measure this. But we can start increasing the temperature in Kelvin and looking at the equation of this line, and it goes through 0 every time. So what this tells us is that volume of the gas is proportional to temperature if you're in Kelvin, or Rankine if you feel the need to use the Fahrenheit version. But if we're in an absolute temperature scale, if you double the temperature, you double the volume of the gas. Right? Because that proportional, this symbol here, means it's a straight line and it goes through 0. Right? So Charles' law starts from this, which is another way of stating volume is equal to a constant times temperature. In other words, it's a straight line with no y-intercept. Right? If you think about this as y equals mx plus b, the regular form of a straight line, y is volume, k is the slope, x is temperature, and b is 0 because it goes through the origin. Right, and so then if we do the same thing we did for Boyle's law, where we said, okay, I'm going to just rearrange it, so I'm going to put the constant by itself.
we put the constant by itself, we can do the same thing we said before, where we say, okay, well, any volume divided by its corresponding temperature is equal to a constant, and any other volume divided by the corresponding temperature is equal to that same constant. Right, so this is Charles' law. I'm not going to test you on the names of them. I mainly just think it's funny because I'm a fan of Brooklyn Nine-Nine, that the first two laws of gas laws are Boyle's and Charles'. I don't know that that's in the writing on purpose, but I choose to believe it is. All right, so let's do a practice problem. Sealed 1 liter system is heated from 22 Celsius to 51 Celsius at a constant pressure. What's the new volume? So volume 1, 1.0 liters. Volume 2, we're trying to find. Temperature 1, actually, write it down here. 22 degrees Celsius. Temperature 2 is 51 degrees Celsius. The only tricky part about this equation is the temperatures have to be in Kelvin for this to work. This equation only works if this line goes through the origin, like we talked about, so it has to be proportional for this to work, which means our temperatures have to be in Kelvin. So we just add 273 to both of these. We get 295 Kelvin and it's at 374 Kelvin. Now we know everything except V2. A little bit of algebra, we're good to go. So V2 is equal to V1 over T1 times T2. Again, in Kelvin. So 295 times 1, or 1 over 295 times 320, 37. No, I messed that up. That's 324. How could you let me do that? I can add 50.
So we need to.
We'll only get, so for these ones, we get to keep 3 sig figs because we added to the conversion. So we keep the uncertainty in the ones place. We actually picked up a sig fig on our temperatures, but our final answer is only going to have 2 sig figs because of that 1.0 liters. So V2 equals 1.1 liters. If you tried to plug in Celsius here, there's not a dead giveaway. You have to remember to put it in Kelvin because there's no obvious red flag here. If you plugged it in Celsius, though, we more than doubled the temperature in Celsius, which would give us our final volume is more than 2 liters. That's way different than what we actually see, right? So this is one of those ones where if you get a temperature, put it in Kelvin. Right, the only time that Kelvin and Celsius are interchangeable is with that delta T term. A delta T, it doesn't matter if you're in Celsius or Kelvin, you're going to get the same delta T. So for Q, we can use Celsius. Everything else, we're going to use Kelvin.
So that way for the Kelvin is absolute temperature.
Yeah, we have to put it in absolute temperature, which is Kelvin. All right, so absolute temperature just means that 0 corresponds to absolute zero. Zeroing whatever your temperature units are. We're just basically going to stick with Kelvin. Nobody uses Rankine. I've never met a person or an application or read a paper that used degrees Rankine in any sort of way. So just put it in Kelvin. All right, so we know that changing the volume changes the pressure. We know that when the temperature changes, the volume changes. This also actually means that we can change the volume into the temperature changes. We're used to thinking about we can control the temperature and watch how something else changes, but this actually tells us we can go the other way. If we keep it at the same pressure, we can change the volume, and that will change the pressure. Sorry, we can change the volume, that will change the temperature. Which is a little bit weird to think about. That's not how we usually think about temperature. If we wanted to see how pressure and temperature were related, we could expect something pretty similar to this, right? If we were holding the volume constant, then A doesn't change. But doubling the temperature would mean the force doubles too. So we don't want to do that experiment though, because that's how you blow stuff up. We don't really want to blow stuff up usually. So we can actually just use classical geometry, going all the way back to Euclid's axioms. One of Euclid's axioms I want to say Euclid's axioms goes back to what, 4000 BC? A really long time ago, predating Aristotle and all that. If A equals B and B equals C, A equals C, right? I think is that the transitive property thing. I don't know. I'm not correct on all my names of all the various properties, but we can all agree that that's true, right? It turns out you can do the same thing with that proportionality symbol. So if A is proportional to B and B is proportional to C, then A is proportional to C. I'm not going to make you do this derivation yourself at any point, but just to show you where these equations come from. So if volume is proportional to temperature and pressure is proportional to 1 over volume, those two laws we already looked at, we can basically write the same exact equation as the Charles law, except with pressure in there instead of volume. So pressure 1 over T1 is equal to pressure 2 over temp 2, as long as you're in Kelvin. It means we can do more examples. CO2 liter bottle is left in the car on a hot day and reaches the temperature of 48 Celsius. If the pressure is initially 610 torr and the initial temperature is 27 Celsius, what is the final temperature, final pressure in millimeters of mercury? It's just the same as the last two examples we did, just with different units. Getting to recognize the units becomes really important because it's really easy to tell which version of these simple gas laws we have to use, as long as you know, oh, millimeters of mercury, that's pressure. Celsius, that's temperature. I know I have to use this version, right? But the really interesting things happen when we start combining these things. Because if we can say that these different simple gas laws are all true individually, we can actually start plugging them all together. So the combined gas law looks like this. Pressure 1 times volume 1 over temperature 1 equals pressure 2 times volume 2 over temperature 2. Now we've got it so that everything can be changing at once. This looks like a more complicated equation, and it is, But don't panic because I still have to give you 5 out of the 6 pieces to be able to solve this, right? If you're actually going to get a number for the unknown, I have to tell you everything else except the unknown, right? Or else you can't solve it. So these more complicated word problems, I have to give you more information so you still can figure out what version you're going to be using. A balloon is treated as a closed system, i.e. constant number of molecules. If a balloon is initially filled to 1.05 atmospheres at 22 Celsius and has a volume of 5 liters, those are all my initial conditions. So that's pressure 1, volume 1, temperature 1. Then you leave the balloon in the sun. Temperature changes and the volume increases. I had to give you 5 pieces of information in order to solve for the 6th. But once you know all those pieces, plug everything in, solve for whatever you're missing. So in this case, P1, 1.05 ATM. B1, 5.0 liters. T1, 22 degrees Celsius, which is 295 Kelvin. Because we all remember that Kelvin is equal to Celsius plus 273. If you don't remember that, why you have an equation sheet, right? Sitting right there in your conversions. So you don't have to have that memorized. B2 is 5.1 liters. T2 is 34 Celsius plus 273. Is that 311? No, 307, huh? We plug it all in and we solve for P2. Know the units and which variable they go with. And these are all the same, essentially. Figure out if I'm talking about before or after. Make sure your units are all consistent. Make sure all your temperatures are in Kelvin and you're good to go. There's one more variable that can affect pressure and volume and temperature with all these. What's the one thing we've been holding constant this whole time for all these equations to work? Say it again.
Mass.
Mass of what?
Yes.
Yeah, or in other words, number of gas molecules. Turns out it doesn't matter what the mass of the gas is, because temperature is proportional to kinetic energy, which has the mass factored in. So it doesn't actually matter what the mass or the molar mass or the total mass of the gas is. It just matters how many gas molecules are there. And so here's our last combined form here. This is the final form. Goku Dragon Ball Z style. Put all of this together. We get one combined gas law. The pressure of a gas times the volume of the gas divided by the temperature of the gas in Kelvin divided by moles of gas molecules is always equal to the same form on the other side, P2 V2 over T2 N2. As long as one thing is held constant, this is the only form of the combined gas laws you need. If you check your conversion sheet, your equation sheet, it doesn't have just Boyle's law. It doesn't have the individual form of any of these gas laws. It just has this. Because this is the only form you need, because for Boyle's law to work, for this to work, we had to assume two things. And I said them kind of quickly in passing, so you might not have caught it, but we were assuming N is constant. We're assuming that because I said it's a closed system, so the number of gas molecules change. And we're assuming that temperature is constant. How does this get us there? Well, if N's constant on both sides, before and after, if N1 is equal to N2, I can multiply both sides by N and they'll cancel out, right? And if temperature is constant, before and after, if T1 is equal to T2, I can multiply both sides by the temperature and temperature cancels out. So at whatever is constant on both sides of the equation, you just cross out that variable. If moles is constant and temperature is constant, those go away. We just get this. Or if volume is constant and moles are constant, volume cancels volume, moles cancels moles, and we get pressure 1 over T1 equals P2 over T2, which was that other one we just discovered, right? So basically, this is the only form you need on your conversion sheet. Whatever is held constant, you just cross it out. There's one more important implication here. These are the 4 variables that kind of define a gas. If we take any gas, contained or not, or keeping things constant or not, any gas, if you take the pressure of that gas times the volume of that gas, divide by the temperature in Kelvin, and you divide by moles, it always gives you the same constant. Any gas. Any gas in any container. So if any gas gives you the same constant, we're not limited to just looking at before and after. We can actually just say, no matter what, a pressure times a volume over moles over temperature is equal to the same constant that we call the ideal gas constant. So this is where gases this is 9 times out of 10 for any of the science classes that you're going to take in the future, unless you're going into engineering or chemistry. This is the version you're actually going to use. We rearranged this so that it doesn't have a fraction, because who likes fractions? Nobody likes fractions, right? So we just multiply both sides by N and T. We get pressure times volume equals moles times R times T. This is the equation you're going to use 9 times out of 10. Because this means as long as you know pressure, volume, and temperature, you know how many moles you have. Or if you know moles and temperature and volume, you know what the pressure is. As long as you know 3 of those variables, you can figure out what the last one is. So somebody's question on the quiz was, how did they initially figure out all of these mole-to-mole relationships before they had modern instruments? because they could measure atmospheres of gas and they could measure volume and they could measure temperature. As soon as they figured this out, this opened the door for Dalton's atomic theory to take over. Because this was our easy way of figuring out how many moles we had of something. Doesn't seem as easy as weighing things, but if you don't know what those atomic masses are, you don't know how the atomic masses work, but you do know that gas molecules behave in this totally random way where it doesn't matter what the gas molecule is, it bounces off of stuff. You can figure out how many moles you have. And it doesn't matter what the gas is. Doesn't matter if it's oxygen, if it's hydrogen, if it's nitrogen, or if it's CO2, anything. Whatever it is, as long as you know your moles, you know temperature, you know 3 of those variables, you can get the last one.
So Kelvin is based off of the scale of Celsius, which is based off of water. Is it just happenstance that that scale actually works with the doubling factor for volume?
No, because any scale that we use, as long as we started it at 0, would work for these. So we used Kelvin and defined the difference in temperature of 1 degree Kelvin to be the same as Celsius. So we didn't have to change a bunch of textbooks, basically.
Right.
But any temperature unit would work as long as it starts as 0 and that temperature unit is absolute 0. All right. The other nice thing about this is we know what that number is. Turns out R is one of those fundamental constants of the universe that Einstein was trying to shoehorn all into one comprehensive theory of everything. And then Hawking took over that, and physicists are still trying to reconcile all the different like random numbers, like speed of light and things like that, into one cohesive theory that ties all the different fundamental forces together. R is one of those constants that shows up all over the place. And in gas laws units, it's 0.08206 liters times atmospheres per mole times Kelvin. This is one of the cases where the constant units don't make a whole lot of sense. They basically are there to cancel everything else out. So if you're using this version of the equation of the gas laws, now all of a sudden we do care about what units everything is in, because we need the right units to match R. If you had access to the internet, if this wasn't on the timed portion of the test, there's a 1,000,001 versions of R where they're just different combinations. There's a value for R where instead of liters, it's gallons, and instead of atmospheres, it's PSI. And instead of Kelvin, it's Rankine. That's just gonna have a different number, but it's always gonna be a volume unit times a pressure unit over moles over absolute temperature unit. As long as our pressures all of our variables are in the right units, we just use this one. So rather than have a whole bunch of different R values that you have to memorize or look up which one to use, I only put one. I guess there's 2 on your conversion sheet. Only one that's in gas line units though. The other one is it's in joules per mole Kelvin, and we use that when we're talking about energy more. So it turns out joules per mole Kelvin is actually an entropy unit that has to do with randomness, and so that's one of the other places. It's like we're working all this, where we see R show up is in thermodynamics, is in talking about heat and energy. All right. Let's practice using this equation real quick, and then we'll be done for the day. Scuba tank has a volume of 15.0 liters. It's filled to a pressure of 200 atmospheres at 22.5 degrees Celsius. How many moles of gas are in the tank? We know pressure, we know volume, we know temperature, we know R. So, and again, I don't usually write it like that. Most textbooks are going to write it like this. It's the same exact equation though. I just rearranged algebraically. So 200.0 ATM times 15.0 liters equals moles, which is what we're trying to solve for, 0.08206 liters, atmospheres per mole, Kelvin. And our temperature in Kelvin is 295.7 Kelvin. Solving for N. Get 3,000 over 10. So 30,000 over 300-ish. Something about N is going to be around 100, I think. 80 maybe. No, 120, 124. All right, let me wipe this out and I'll show the algebra for it. So because that'll help us with the units too. 15.0 liters equals moles of what we're solving for, 0.08206 liters ATM per mole Kelvin, 295.7 Kelvin. So Kelvin's going to cancel Kelvin right away. That's going to help things out. We're going to divide both sides by 0.08206. Liters ATM per mole now. Cancel out the Kelvin on the 295, but we're still going to divide by it. I made that look really messy. Then we've got liters on the bottom, liters on the top, atmospheres on top, atmospheres on bottom. Everything cancels out for our units, except we get 1 over moles as our final unit. So 124 when we plug all that in. And just a reminder, we divided by that over here. So that cancels that. That all cancels. Reminder, anytime you get units that look like this, when you divide by a fraction, that's the same as multiplying by the reciprocal, right? So if I said 1 over 1 divided by 1 over moles, when we multiply our fractions, we flip the second number and this turns into multiplication, right? So we get 1 over 1 times moles over 1. So our final units are just moles. Okay, just if you're not sure how this turns it, it's just the same as moles. That's what's going on here. We're dividing by a fraction. So we get moles winds up on top again. All right, remember how I said that the rest of this class, I'm going to teach you some more properties and then I'm going to teach you how you can use it to find moles. Where do you think we're going with this equation next? We can use PV equals nRT to do stoichiometry problems. Right? This is just one more way we can get to moles or get from moles into something we can measure at the end. So we'll do practice with that on Wednesday.